It's July 16th, 1945, 5:29 a.m. You're standing in the New Mexico desert 10 miles from a steel tower in the middle of absolutely nothing. You're wearing welder's goggles. Your hands are shaking, not from the cold. From the fact that you and about 200 other people scattered across this stretch of sand genuinely do not know if you're about to witness a failed experiment or the last morning of the human species. Somewhere behind you, the physicist Enrico Fermi is tearing small pieces of paper and holding them above his head, ready to drop them the moment the blast hits so he can estimate the yield from how far the scraps travel. That's not a joke. One of the greatest scientific minds of the 20th century is about to measure the most powerful explosion in human history with confetti. In about 60 seconds, a device roughly the size of a large car is going to release more energy than 20,000 tons of TNT. And the chain of events that made that device possible started not in a weapons lab, not in a military bunker, but in the mind of a patent clerk in Switzerland who was thinking about light. So how did humans go from understanding nothing about atoms to detonating one in a desert in roughly 40 years? The answer takes us through a half-century sprint of physics, an accidental discovery that terrified the people who made it, a secret industrial operation larger than the American automobile industry, and one haunted physicist who spent the rest of his life wishing he could take it all back. Let's start with what an atom actually is and why splitting one releases energy. Because if you don't understand this part, nothing else in the story makes any sense. For most of human history, we assumed matter was continuous. You could keep cutting something in half forever. The ancient Greeks had a word for the smallest possible piece of something, atomos, meaning uncuttable. Nice idea, completely wrong about the details, but the intuition that matter has some kind of smallest unit turned out to be roughly correct. By the late 1800s, physicists had figured out that atoms were real and that they weren't actually the smallest things. They had internal structure. In 1897, J.J. Thomson at Cambridge discovered the electron, a tiny negatively charged particle inside the atom. Then in 1911, Ernest Rutherford, a New Zealander working in Manchester, fired alpha particles at a thin sheet of gold foil and found that most went straight through, but a small number bounced back at extreme angles. His own reaction is worth quoting. He said it was as if you fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. What he discovered was the nucleus, a dense, positively charged core at the center of the atom, containing almost all of its mass in a space roughly 100,000 times smaller than the atom itself. Now, here's where the story turns toward the bomb, because understanding that the atom had a nucleus meant people could start asking what happens if you mess with it. In 1932, James Chadwick, also working at Cambridge, discovered the neutron, a particle sitting inside the nucleus alongside protons but carrying no electric charge. That last detail is everything. Because protons are positively charged, they repel each other. Trying to force a proton into a nucleus is like trying to push two magnets together at the wrong end. But a neutron has no charge. It can slip right in, there's no electromagnetic barrier, it just walks through the front door. And once it's inside, it can destabilize the entire nucleus. Think about what that means. A particle with no charge, discovered in a university lab in England, turned out to be the key that could unlock the energy stored inside matter itself. Chadwick didn't set out to find a weapon component. He was trying to understand what atoms were made of. But once you know that neutrons can penetrate nuclei without resistance, the next question becomes unavoidable. What happens when they do? The answer came 6 years later, and it terrified the people who found it. In December 1938, two German chemists, Otto and Fritz Strassmann, were working at the Kaiser Wilhelm Institute in Berlin. They were bombarding uranium with neutrons to see what new elements might form. This was a standard experiment at the time. You throw particles at heavy atoms and see what sticks, but when they analyzed the results, they found something that didn't make sense. Instead of creating a slightly heavier element, the uranium had split into barium, an element roughly half the mass of uranium. That shouldn't have been possible. It was like throwing a marble at a bowling ball and having the bowling ball crack in half. Hahn wrote to his former colleague Lise Meitner, an Austrian physicist who had fled to Sweden months earlier to escape Nazi persecution. Meitner and her nephew Otto Frisch worked through the physics over Christmas in a small Swedish village, sitting on a tree trunk in the snow doing calculations on scraps of paper. They realized what had happened. The neutron hadn't just chipped a piece off the uranium nucleus, it had split it apart entirely, and when they calculated the mass of the two resulting pieces, those pieces weighed slightly less than the original uranium atom. That missing mass had been converted into energy, following Einstein's equation from 1905, E equals mc squared. Now, Einstein published that equation as a theoretical insight about the relationship between mass and energy. He was not thinking about weapons. He was thinking about the fundamental nature of reality. But the equation says something terrifying when you apply it to actual atoms. Even a tiny amount of mass converted fully to energy releases an enormous amount. The speed of light squared is roughly 90 quadrillion. Multiply even a tiny fraction of a gram by that number, and you get an explosion. Frisch named the process fission, borrowing the term from biology where cells divide in two. Within weeks, the news had reached physics departments across Europe and America, and the reaction was not excitement, it was dread. Because every physicist who read Meitner and Frisch's paper immediately understood two things. First, fission released energy. Second, if fission also released extra neutrons, those neutrons could hit other uranium atoms, causing more fission, releasing more neutrons, causing more fission. A chain reaction, and a chain reaction in a large enough mass of uranium would release all that energy not over hours or days, but in a fraction of a second. That is a bomb. In January 1939, the Danish physicist Niels Bohr arrived in New York for a conference and brought the news of fission with him. Within weeks, research groups at Columbia University, the University of Chicago, and several European institutions had independently confirmed the results. Fission was real. Chain reactions were theoretically possible. And the most terrifying government on Earth at that moment, Nazi Germany, was where the discovery had been made. Here's where the politics collide with the physics, because everything that happens next only happens because of fear. In August 1939, Albert Einstein, a pacifist who had fled Germany in 1933, signed a letter to President Franklin Roosevelt warning that uranium could be used to construct extremely powerful bombs and that Germany might be working on exactly that. The letter was drafted largely by the Hungarian physicist Leo Szilard, who had actually conceived of the nuclear chain reaction idea years earlier, in 1933, while crossing a street in London. Szilard had been so alarmed by his own idea that he'd tried to patent it and keep it secret. He failed. The science was spreading too fast. Roosevelt read the letter. He formed a committee. The committee moved slowly at first, because in 1939, the idea of an atomic bomb still sounded like science fiction to most politicians. It took 2 more years, and the entry of the United States into World War II after Pearl Harbor in December 1941, before the project received the kind of funding and urgency that matched the scale of what was being attempted. And the scale was genuinely absurd. In June 1942, the U.S. Army took control of the bomb project and assigned it to Brigadier General Leslie Groves, a military engineer who had just finished overseeing the construction of the Pentagon. Groves was blunt, impatient, and extremely effective at building large things on impossible timelines. He named the effort the Manhattan Engineer District. It became known as the Manhattan Project. Think about what they were trying to do. They needed to build a weapon based on physics that had been confirmed only 3 years earlier, using materials that didn't exist in usable quantities, with engineering that no one had ever attempted, on a deadline set by the possibility that Hitler's scientists might get there first. And they needed to do all of this in total secrecy. Groves made 2 immediate decisions that shaped everything. First, he recruited Robert Oppenheimer, a theoretical physicist from Berkeley, to lead the scientific effort. Oppenheimer was brilliant, charismatic, spoke 6 languages, read Sanskrit for fun, and had absolutely zero experience managing anything larger than a graduate seminar. Groves picked him anyway because Oppenheimer understood the physics deeply enough to coordinate dozens of competing scientific teams, and because he could talk to both physicists and generals without either side walking out of the room. Second, Groves built cities, not laboratories, cities, because the first problem, before anyone could even think about building a bomb, was getting enough fuel for one. Here's the problem that doesn't get enough attention because it's not dramatic, but it's the reason the bomb was an industrial achievement as much as a scientific one: natural uranium. The stuff you dig out of the ground is mostly uranium-238, over 99% of it. Only about 0.7% is uranium-235, the isotope that actually fissions efficiently with slow neutrons. To build a uranium bomb, you need to separate U-235 from U-238, and here's the thing that made everyone's head hurt. These 2 isotopes are chemically identical. They're the same element, same number of protons, same number of electrons, same chemical behavior. The only difference is that U-235 has 3 fewer neutrons, making it slightly lighter, about 1.3% lighter. Separating 2 things that are chemically identical and differ in mass by barely 1%, at industrial scale, in secret during a war. That was the actual challenge, not the physics. The physics was done in a few years. The engineering took 2 years and $2,194, roughly $30 billion in today's money. Groves built an entire secret city at Oak Ridge, Tennessee. At its peak, the Oak Ridge facility employed over 75,000 people, most of whom had no idea what they were making. Workers operated massive machines in enormous buildings, following precise instructions, handling materials they couldn't name, producing a substance they'd never heard of for a purpose no one would tell them. The entire complex used more electricity than New York City. One building, K25, was the largest building under one roof in the entire world at the time. It used gaseous diffusion, pumping uranium hexafluoride gas through thousands of barriers with microscopic pores, letting the slightly lighter U-235 molecules pass through marginally faster. Over and over and over. Thousands of stages in sequence, each stage increasing the concentration by a tiny fraction. There was a second method running simultaneously, electromagnetic separation, housed in buildings called calutrons. These used massive magnets to bend streams of ionized uranium atoms. The lighter U-235 atoms curved slightly more than the heavier U-238 atoms, allowing them to be collected separately. The calutron magnets required so much copper wiring that the Manhattan Project borrowed 14,700 tons of silver from the US Treasury to use as a substitute because there wasn't enough copper available during wartime. Silver from the National Reserve melted down and wound into electromagnetic coils to separate atoms. That sentence should sound insane because it is. While Oak Ridge was enriching uranium, a second secret city was being built at Hanford, Washington, along the Columbia River. Hanford's job was producing plutonium, an entirely different path to the bomb. Plutonium-239 doesn't exist in nature, you have to make it. You do this by putting natural uranium into a nuclear reactor where neutron bombardment transmutes some of the U-238 into plutonium-239 through a series of nuclear reactions. Enrico Fermi had demonstrated the first self-sustaining nuclear chain reaction on December 2, 1942, in a squash court under the bleachers of the University of Chicago's football stadium. The reactor was a pile of graphite blocks and uranium, and it worked. Fermi controlled it with cadmium rods that absorbed neutrons. When you pulled the rods out, the reaction sped up. Pushed them back in, it slowed down. The entire future of nuclear energy and nuclear weapons was controlled that afternoon by a man sliding rods in and out of a pile of graphite under a football stadium in Chicago. Hanford scaled this up enormously, building full-size production reactors along the river, using the river water as coolant. The plutonium was then chemically separated from the irradiated uranium in massive processing plants, one of the most dangerous chemical operations ever attempted, handling intensely radioactive materials using remote-controlled equipment because getting close would kill you. And then there was the third city, Los Alamos, New Mexico, a former boys' school on a mesa in the mountains, converted into the most secret weapons laboratory in history. This is where Oppenheimer gathered the physicists, chemists, metallurgists, and engineers who would actually design and build the bombs. The community eventually grew to several thousand people. Families included, all living behind fences with their mail censored and their location officially non-existent. Their address was a P.O. box in Santa Fe. Now, here's where the engineering gets genuinely wild, because building the bomb turned out to be two completely different problems depending on which fuel you used. The uranium bomb was conceptually simple. You take two pieces of U-235, each below the critical mass needed to sustain a chain reaction on its own. You slam them together fast enough that the combined mass goes critical before the thing can blow itself apart prematurely. This was the gun-type design. One piece of uranium fired down a modified artillery barrel into another piece. The physicists were so confident this design would work that they never tested it. The first uranium bomb ever detonated was dropped on Hiroshima. They called it Little Boy. Plutonium was a different problem. Plutonium-239 has a contaminant, plutonium-240, that undergoes spontaneous fission at a high enough rate that a gun-type design won't work. The two pieces would start chain reacting before they fully assembled, producing a fizzle instead of a full explosion. The solution, devised primarily by the mathematician John von Neumann and the physicist Seth Nettermeyer, was implosion. Instead of slamming two pieces together, you surround a sphere of plutonium with carefully shaped explosive charges. When those charges detonate simultaneously, the shock wave compresses the plutonium sphere inward, squeezing it to several times its normal density, making it supercritical in a fraction of a microsecond. The problem is that simultaneously means simultaneously. The explosive lenses surrounding the plutonium core had to detonate within 1 microsecond of each other, or the compression would be uneven and the core would squirt out the side like squeezing a wet bar of soap. Designing explosive shapes that could focus detonation waves inward with that level of precision was one of the hardest engineering challenges of the entire project. George Kistiakowsky, a Ukrainian-born chemist, led the explosives team, and the number of failed test shots, misfires, and uneven compressions his team worked through before getting it right is staggering. This was the design they had to test, because unlike the uranium gun type, nobody was confident implosion would actually work. Which brings us back to the desert. The test was called Trinity. Oppenheimer chose the name, possibly from a John Donne poem. The device, called the Gadget, sat on top of a 100-foot steel tower at the Trinity site in the Jornada del Muerto desert, which translates to Journey of the Dead Man. The name wasn't chosen for dramatic effect. That's just what the Spanish called that stretch of desert centuries earlier, because crossing it could kill you in the hours before the test. It rained. Lightning struck near the tower. Scientists debated whether to postpone. Bets circulated on whether the bomb would work at all. Edward Teller took the optimistic position. Fermi, half-joking, offered to take bets on whether the bomb would ignite the atmosphere and destroy the entire state of New Mexico. He later said he was kidding. Some of the people standing near him weren't completely sure. At 5:29 a.m. on July 16, 1945, the gadget detonated. The flash was visible from 250 miles away. The mushroom cloud rose to 40,000 feet. The steel tower evaporated. The sand beneath it fused into a new material, a glassy green substance later named Trinitite. The shockwave broke windows 100 miles from the blast site. Fermi dropped his scraps of paper, watched how far they traveled, and estimated the yield at roughly 10 kilotons. He was close. The actual yield was around 21 kilotons. Kenneth Bainbridge, the physicist who directed the test, turned to Oppenheimer and said, "Now we are all sons of bitches." Oppenheimer later said he thought of a line from the Bhagavad Gita, "Now I am become death, the destroyer of worlds." Whether he actually thought that in the moment or constructed the memory later is something historians still argue about. What's not debatable is what happened next. 3 weeks later, on August 6, 1945, the untested uranium bomb, Little Boy, was dropped on Hiroshima. 3 days after that, a plutonium implosion bomb, Fat Man, identical in design to the Trinity device, was dropped on Nagasaki. Together, the two bombs killed an estimated 110,000 to 210,000 people, most of them civilians, most of them in the first few seconds. The entire Manhattan Project, from Roosevelt's initial committee to the bombing of Nagasaki, took roughly 6 years. It employed over 125,000 people at its peak. It cost about $2 billion 1945 dollars. It created 3 secret cities, a new element, an entirely new branch of physics, and a weapon that made every previous weapon in human history look like a pointed stick. And the people who built it were, in many cases, immediately horrified by what they'd done. Leo Szilard, the man who first conceived of the chain reaction and helped convince Einstein to write the letter to Roosevelt, spent the rest of his life campaigning against nuclear weapons. He'd petitioned Truman not to use the bomb on civilian targets. The petition never reached the president. Oppenheimer was stripped of his security clearance in 1954, partly because he'd expressed moral reservations about building the hydrogen bomb, a weapon 1,000 times more powerful than the ones dropped on Japan. The government he'd served turned on him for having a conscience. There's something worth sitting with in the full arc of this story. 40 years. That's all it took. From Rutherford's gold foil experiment to Trinity. From the atom has a nucleus to the atom has been weaponized. A chain of discoveries, each one reasonable on its own, each one answering a genuine scientific question, and none of them, not one, originally intended to produce a weapon. Thomson was curious about cathode rays. Rutherford wanted to understand atomic structure. Chadwick was looking for a missing particle. Hahn and Strassmann were doing routine chemistry. Meitner and Frisch were trying to explain a confusing result. Einstein was thinking about the speed of light. Szilard was crossing a street. Every step made sense. Every step was driven by curiosity, by the desire to understand what the universe is made of and how it works. And the thing they collectively built killed more people in 2 mornings than most wars kill in a year. Nobody who discovered the electron in 1897 could have predicted Hiroshima. But every discovery between those 2 points fed the next, and the next, and the next, until a group of human beings stood in a desert in New Mexico and watched the sky turn white and felt the heat on their faces from 10 miles away and understood all at once that they had changed what the word war meant forever. The tools were physics, the fuel was fear, and the result is still sitting in silos and submarines in at least 9 countries right now. Tonight, while you're watching this, roughly 12,500 nuclear warheads according to the Federation of American Scientists. Most of them far more powerful than anything dropped on Japan. The people who split the atom were trying to understand it. The people who built the bomb were trying to end a war. The people who tested it in the desert that morning were not cheering, they were quiet. Some of them were crying. And one of them, standing in the pre-dawn dark with the light still fading from the sky, said the only honest thing there was to say. Now we are all sons of bitches.